As of this morning, RICAIP has grown substantially. We have added, with the signature of the Memorandums of Understanding, 2 new associate partners who will introduce their visions today. And I'm very grateful to start with Professor Steffen Ihlenfeldt from Fraunhofer IWU. And I hand over.
So, once again, thanks for the invitation for the meeting today and involving us into your network. So it was not that we asking you, you asking us, and so we are very happy to join this team. And again, maybe one short comment to your presentation. I'm really happy that you already talk about Industry 4.0. So I had a long discussion with Peter Liggesmeier, and he's so concerned that everyone talks about 5.0, and you mentioned here there is an idea behind 4.0 and all the topics what someone else connecting with 5.0 did already in this idea, and so we have to have the idea, and it takes time. A revolution is not ready after 1 year, so we have a vision for the next 10 years, and so so I step now into production systems, and maybe some points I put into your direction. You often what we already have seen is assembly processes, and we had already had all the discussion when we go to machining, to cutting, and so we have to integrate the physical behavior. So it's not just is this step already done, so is it in the right way done, and which information do we need? So we have this concept of cognitive production systems, and I want to give some implementation examples on machining. And so I would like to start with overview about future production with cognitive production system, and step into the machining processes, and have also a outlook to human-robot interaction, because there's a huge topic here in Prague. And so that's now. But at first, so we joined this team here, and just some words about Fraunhofer IWU. So we are located in Chemnitz, Dresden, and also in Zittau. So this really close to Prague, and that's why we have this running collaboration. We have also a center in Wolfsburg. Maybe we can discuss this, how we can use this Fraunhofer Project Center is also a public-private partnership concept, and maybe these topics we can also test. We are founded in 1990, and now we are roughly 670 employees, and so all the topics we have heard already, we have also in the IWU, so the research efficient production. So this is also a topic we had a large project with Volkswagen. So it's not just the shutdown to start your machine again. Often the real problem that when we have a planning for energy efficiency, and you find out that there's a possibility to go in standby, then you have to start your machine, and this makes often the problem. We had a project with BMW, and there were just marks at a machine, which machine you can switch off and which not, and these are the real problems when you go to Industry 4.0, that sometimes the machinery is not ready for the good ideas we have, and so this is where we're working on. And when we look at the requirements for the future, so we can discuss a lot about the topics like environment and the sustainability and so on, the role of humans, how we change it, the role of humans here in maybe in Europe. Is it available, or how is it what is with aging and so on? So these are the topics we are focusing on, and everyone do this. And so I'm quite happy with your speech, because we have the same idea. The factory of the future will be an urban factory. The factory of the future will be an urban factory. Is because of the short way to the factory, but also all the creative processes are in the city. The creative people live in the cities, and so we have to bring the creativity into the factory, and so there are lots of topics we expecting when we have factories as urban factories. But we need to handle with the CO2 emission. So we say it's not just zero. Maybe we can also CO2 negative when we integrate it in the right way. So we have to use local resources. We have to close the circuits in the city, not just in the factory, but with a view at the city itself. And could be also a product for European manufacturer or communities, because the idea of urban factories is especially for larger cities worldwide. When we look to Asia, so we have to integrate factories in urban environment, and to close the do I something?
Yes, I need to change the microphone. I don't know. Can you hear it? It's real bad.
Okay. I try to do my best. And now, it's a bit loud. We have to manage this. And the topic today is the factory of the future is not just producing products, they produce also knowledge. And this is what we already talked the whole day today, and that's why we call it cognitive production systems. And when we compare human beings and the machine processes, we have lots of interactions and same idea. So we have this, we have the self-reflection. We work it in an efficient way. We want to do it independent, and of course we are able to adapt to some changes in the process. And this is what we have to link also to the production of the future. And so this, when we say how we can do this, what is the technical cognitive systems, we find lots of things. For example, we have to develop dialogue systems between human and machine. We need machine-readable self-optimization strategies. Of course, we need the self-description, what we already have solved with, for example, BASIS and so on. So some of the topics we already have done, some we have to develop in the future. And so we have created an idea of human cyber-physical production systems. So we have to combine the technical cognition and the knowledge from the worker, the knowledge from the developer of products. And this is what we have to bring together in the next step. This is, or could be also a part of the next 10-year topics. So, and for this we have to develop sensory solutions. We need technical neural systems, we need a self-awareness and biointelligence. These are the topics for the next years. And I want to show you some results, what we already solved in the process chain of machining processes. So normally we start with CRD, CRM system, CNC. We have the process with machine process interaction. Then we have the measuring, and then have the workpiece. This is the process chain we have already here. And what we realize is, of course, a quality forecast when we want to close your loop. So we don't want to have a measurement device at each step. Sometimes it's good enough to have the sensory data and the knowledge, and then we can do a forecast for the quality, and this reduces also the effort. And for this, so you know, there are different definitions of digital twins, and one is that we use the data from the machinery, combine this with physical models, and then we can predict the quality from the part. And for this, we are working on that we can implement this in, especially for serial production now, and then future for just single part production. This is what we are working in, and for this you need all the topics, which data you need, can you compress the data, so which information you need from the process planning, which information do you need from logistics and so on, and all this we have to match. And I think we have a longer presentation today from Albrecht Henel later on. He will also show this concept here, how we use the database, which format we need, and how we extract then together with the simulation coming to the real physical digital twin. And the next step, this is what we have done with the part of the process, the machine process interaction. On the other hand, you have the machine itself. And so you have to qualify the machine to the cutting machine to a measurement device. So you need models for example, for thermal behavior, for the dynamic, for the static behavior. Combine this with additional measurement devices, and so you have not just the deflection from the tool, so you have also the deflection from the machine itself. And when you combine this, you can predict the quality. This is our approach, and this is, I think, we have to do a lot of work together. So we are quite happy that we start now a project with Peter Higgesmeier together to implement this to Basis 4.0 to the physical layer for the cutting processes. This is, we are quite happy, but already we can see also first results. The next topic is how you can self-describe the machinery, and for this you need the self-diagnosis. One traditional approach is that you have some dry runs of the machine, collect the data, and making condition monitoring. But you not just use the condition monitoring for planning of the taking the machine in a good shape, but you have to use this information for self-description and using for the machine process itself, and to run these tests not just with a trial run, so collect the data out of the process itself, then you have to do the identification. Do you have enough excitation for the parameters you want to identify, and then you can use this information, and you have just one simple steps in the process and use this for the data analysis. And next topic we work on is how we can integrate the knowledge from the machine tool user. And we have the topic of acoustic emission. So we run some tests with acoustic emission sensors, and sitting together with all of the user of the machine in our test lab and asking them, is this a stable process, is it a good process or not, just from hearing, using their knowledge, and then we combine this with the acoustic emission, and we bring this together, and there's some interesting results, but so this is ongoing topic now, how we can match this, how we can use this information as an assistance system for the machine tool users, and also to compress the data, because just some frequency range is relevant for the process itself, and that is what we can learn from the machine tool user. And for when we go into not just for the quality prediction, also in the description of the machine itself, we need models for a live simulation. So for this you need very fast simulation models, and you go from finite element models to model order reduction, that we can model the behavior in real time, and then we can mix this to planning information from Industry 4.0 approaches. Then we can match this when we say we go to the shutdown, then we have to calculate, for example, the thermal behavior. Can we switch on the machine again after 10 minutes, or do you need longer than just switching on and warming up to have good quality? This is why we need the physical layer in the future. And then we have to adapt the process because of some changes. So we have uncertainties in the processes itself, so we are lubrication and so on, so, and you have to dealing with these problems. When we, for example, one example is the stability, and you have lots of uncertain parameters in the stability prediction. And our approach was that we running some simulation. So and the result. So I jump directly into the result. So you have confidential intervals for your prediction, and this is exactly what you need when you lively adapt the process. You combine this with sensory information, and when now you have find out that you're in an unstable area, and when you have these confidence intervals, you can make the decision in which direction you have to adapt your process to go to the fastest way in a stable area. This is why we need have to do combination with high performance computing and the topic of self-adaptation. A topic we address in our institute is to bring more sensory in the machine tool, and we start from the sensory tool direct at the cutting edge, to a smart tool, to a sensory spindle or a platform, and we make the decision which sensory is the right way for the process. This knowledge you need, and you need this case, so you need all this solution, and you need the knowledge to make the decision which is the right solution. For example, what you have to do, you have this information. This is not enough. At the end, you have to make the decision which sensor information are relevant for condition monitoring. Not all of the information are relevant, so you have to use it online, make the decision online, and use just this information for the condition monitoring. And if you have this, you can automatically adapt your processes. And a final example where we already bring together all of these information was a really high-level product. This was for space industry, a process of additive subtractive machinery. So you use a optical bench, and this is a really high performance product, and we have make the decision how we can realize that the first part is the right part, and for this you have to adapt your processes. You have to adapt your processes so that you can learn from step by step in this process. How is the behavior of your machinery? How is the behavior of the material? What you're machining? What is the state of your tools? And for this, you can realize a first-time right production. And all this we have connected with a large machinery from Rhein at an SME company in Germany. So this is well equipped with all of the sensory from the machinery side. We have adapted also a edge device from Siemens, collecting the data and using this data online to adapt the process, and so we can realize this high-end product also to have a first-time right product. This, when you look at in the future, you heard about Athena. This is exactly this product. And now I want switch to human-robot collaboration. You have the human skills, and you need technical skills, and you have to bring this in the right way together. And we have seen it. The coffee bar, the right way is that you have hybrid teams. Not just a fully automated system, you need hybrid system, because you have them at the end someone who can solve problem what you not had in mind at the beginning, and for this you need this collaboration. And for this collaboration you need also not just for lightweight robots, also for heavy robots, the online safety zones. And this is what we have developed a system for online adaptation of the safety zones, and so we can increase the speed. This is the topic. The topic is not to have a safe solution. You need a safe and efficient solution. And for this, we have already had a solution. Another solution was that we have a industrial speech system for machine-man interaction. We have realized with lots of companies here in Germany together, and so we can communicate with the machine with real, normal human speech. This is also a topic. They stopped my presentation because I am running out of time. They stopped the. Yes, could you? So this, another, we also work together with Volkswagen. This is an example where we teach robots just by human actions, and this is a solution already runs there. Oops, now it's then we have also optimized this topic. Also, often the main topic is that we have an application and we have to analyze it. Is it better to have this human-machine interaction, or do you have a fence? And then you have to optimize the times. And this brings me to the end of my presentation. Also we have maybe in 2 years or in 3 years an opening ceremony. We have a Center for Cognitive Production System in Dresden plant. So that's why we can really collaborate. So in 3 years we can open this there, and then we, in the meantime, we can vertical collaborate with the 5G lab in Dresden and so on. I think these are really good connections, and now we can start with this. Thank you very much.